All right, so here we're looking at example 4.26. So the first thing we want to figure out is what type of reaction this is. So we have all of our options here. We're looking at the more general classes instead of the 5 specific ones, single replacement, double replacement, etc. So if we look at our context clues, let's figure out what type of reaction this is. So it says how many milliliters of 0.0195 molar HCl, now HCl we know is an acid, are required to titrate. We're going to talk more about this later in the year, and we'll do that as a lab, but a titration is basically a controlled neutralization reaction, so a controlled acid-base reaction, and it's reacting with calcium hydroxide, which we know is a base. So because we have an acid and a base here, we know that this would be an acid-base reaction. So just to make sure we're keeping straight with our classifications of reactions. So in this acid-base reaction, we're going to look at the stoichiometry of this aqueous acid-base reaction. All right, so the first thing we want to do after we identified our reaction type is actually write our reaction. So when we have HCl reacting with calcium hydroxide, HCl is a strong acid, calcium hydroxide is a strong base. So remember, anytime a strong acid and a strong base react, the products are always water and salt, which would be the ionic compound left over. In this case, that's going to be calcium chloride. So there's our reaction. We then would balance it. So to balance this, I would need a 2 in front of the HCl and a 2 in front of the water. So there's our starting reaction. And remember, it's always a good idea to jot down the important information underneath each substance in our reaction. So we had the molarity of our HCl, 0.0195 molar, and it asked how many milliliters of this. So that's what we're looking for. How many milliliters of that are required to react with 10 milliliters of our base, and our base had this concentration, 0.0116 molar. Okay, so that's all of our information from the problem. So the question is now, what do we do with that? Okay, as you remember, or hopefully remember, molarity is defined as the moles of your solute per liter of solution. So if we look at what we have here, we have a volume and we have a molarity. So if we plug in our molarity and our volume converted to liters, we'll be able to find moles of calcium hydroxide. Once we have moles of calcium hydroxide, we can go to whatever we want. So that means we could go from moles of calcium hydroxide to moles of HCl. If we then have moles of HCl, we can plug that into this along with our molarity, and that will give us our volume. Now, if you prefer to use the formula, we can do it that way. You'll have to use the formula once here, then do stoichiometry to get to HCl, and then use the formula again at the end. You can do that, and that is perfectly fine. The way that I'm going to show it is if we do this all in one big problem using dimensional analysis along with our stoichiometry, okay? So that's why I'm going to show it, but please recognize if you set this up differently, that's okay. So if we start with our values here, we're going to start with our calcium hydroxide. Now the question is, which one do we start with? Please remember that molarity is actually a conversion factor. We would have that many moles of calcium hydroxide per 1 liter of solution. So if that's a conversion factor, we're not going to start with that, meaning this is the one we're going to start with, okay? So we're going to start with our 10 milliliters of calcium hydroxide. And we're going to set this up. So first thing we're going to do is we're going to go from milliliters to liters. So we know that there are 1,000 milliliters in 1 liter. So that's going to cancel that. And now we can use our molarity here because we see liters, right? So 1 liter of solution would have 0.0116 moles of calcium hydroxide. Okay, so once we got to moles, the whole point of going to moles was so that we could now use our balanced reaction. So our balanced reaction said that for every 1 mole of calcium hydroxide, there were 2 moles of HCl. Okay, and again, we could stop here and do the formula, but let's just keep going. We're going to use our conversion factor now of this molarity, recognizing that that would be 0.0195 moles of HCl per 1 liter of solution. Okay, so we're going to add on 1 or 2 more steps here. Let me just shrink my math so we can keep going here. All right. Continuing along here, so we're going to use our molarity next. So 0.0195 moles of HCl per 1 liter of solution. Technically, you could stop here. You also could go to milliliters. It does not really matter. I usually go to milliliters just because that's a little bit easier of a number to look at, but totally up to you. All right, per 1,000 milliliters. So to finish it off there, we see liters cancel, moles of calcium hydroxide, moles of HCl, liters of solution, leaving us with milliliters. So when all said and done here, when you calculate your answer, we would use 4 significant figures because, we would use 3 significant figures because 3 in this number, 4 in this number, but 3 in this number. So even though we use these as conversion factors, our molarity will still limit our significant figures. So to 3 significant figures, your answer should come out to be 11.9 milliliters of HCl. So that's how much HCl you would need to completely neutralize all 10 milliliters of our calcium hydroxide. So there's example 4.26. Okay, so now on to example 4.27. If we take a look at this one, it says that we have a vitamin C capsule, which it tells us is ascorbic acid, is titrated. So again, that's another phrase that we'll do in the lab eventually, but that phrase refers to a controlled neutralization reaction. It's reacting with sodium hydroxide, which we know to be a base. So because we have both an acid and a base, that should imply that this is going to be an acid-base reaction. Okay, now how are we actually going to solve said acid-base reaction? Let's take a look at that. Okay, so our reaction for this one, we're not actually going to need all of it, but how we would start, even if you don't know the formula for ascorbic acid, you can just write vitamin C or something like that, just as a placeholder. But we'll have vitamin C reacting with sodium hydroxide, which we know is NaOH, and we're going to form 2 products. Now, ascorbic acid is an acid and sodium hydroxide is a base, so we can guess that our products are going to be water and some kind of salt, which remember is just an ionic compound. It's going to be sodium crossed with something from the vitamin C, but it doesn't actually end up mattering what our products are because all of the important info that we're given, we can just fill in underneath here. So we know that we have 10.30 milliliters of our sodium hydroxide, and it says that the capsule of vitamin C has a mass of 0.518 grams. We also know the molarity of our base, and that was all the information from the problem numerically, but it also tells us that the acid and base react in a 1-to-1 ratio. So why that's helpful is even if we don't know what our products are, if we want to balance our reaction, we know that when we go to do our stoichiometry, we're going to end up with this 1-to-1 vitamin C to NaOH ratio. So that's the important piece. So now let's actually go to solve this. What are we going to do? We are trying to find the percentage of vitamin C in the capsule, but that means that we need to know a mass of just the ascorbic acid, right? So what we're really trying to do is we're trying to convert from all this information about NaOH, so a volume of NaOH, to a mass of vitamin C, so that we can then divide that mass by this 0.518 grams. So since we have molarity and milliliters, we can use our molarity as a conversion factor to get us to moles of NaOH. We'll then use this ratio to get from moles of NaOH to moles of vitamin C, and then it'll be a simple moles to mass conversion at the end. So let's show all that. So to start, again, remember that you could use the molarity formula if you would rather here, but our dimensional analysis will allow us to do this all at once, which is always handy. Okay, so we're going to start with our 10.3 milliliters of NaOH. We'll use our conversion from milliliters to liters. 1,000 milliliters is 1 liter. Then we'll use our molarity as a conversion factor, so 0.250 moles of NaOH per 1 liter of solution. Up to now, milliliters cancel, liters cancel. We have moles of NaOH, so now we can use our 1-to-1 mole ratio between our acid, the vitamin C, and the base NaOH. So for every 1 mole of NaOH that reacts, 1 mole of vitamin C reacts as well. And then if we're trying to get grams of vitamin C, our final step will be to say 1 mole of vitamin C, which we can write our actual formula here, C8H8O6, would weigh, if you calculate your molar mass of that thing, that comes out to about 200.16 grams. So if we check, moles of NaOH cancel, moles of vitamin C, leaving us with grams of vitamin C. As far as sig figs go, we've got 3 here, 4 here, and 3 here. So our limiting number is 3. So to 3 significant figures, we would find that the mass of this thing was 0.515 grams of vitamin C. So in other words, that's how much vitamin C was in this 0.518 gram tablet, which means there's a little bit of filler. So if we want to know the percentage of vitamin C in this capsule, we need to set up a quick division or proportion over here. So we're going to do 0.515 grams of vitamin C divided by the total mass of the capsule, 0.518 grams, multiplied by 100, and that still to 3 significant figures gives us our final answer, 99.5% ascorbic acid. So a good portion of that vitamin tablet is indeed vitamin C. All right, so there we are with example 4.7. Sorry, 4.27. Okay, so on to 4.28. If we look at this one, again, it says we have this volume of HCl reacting with 2.150 grams of sodium carbonate. And even if you're not aware or recognizing right away that sodium carbonate is going to end up breaking down as a gas former once this reaction is involved, what we would know is that because we have HCl involved, we could either narrow it down to an acid-base reaction or a gas-forming reaction. But if we actually go to write our products, our reaction, we'll be able to narrow it down further. So let's think about that. One of our reactants is HCl, and our other reactant was Na2CO3. When we predict our products, if we treat this as double replacement initially, we would get NaCl, and our other product would be H2CO3, which is carbonic acid. So that's what we would get initially. But as you may recall, carbonic acid is a gas former that actually breaks down to form liquid water and carbon dioxide gas. So because we have this carbon dioxide gas here, this is a gas-forming reaction. So when I actually go to write my reaction, we need to write the whole thing, including what's in blue. So let me replace this with our fully written out reaction. Okay, so there's our reaction written with the actual products after the carbonic acid decomposed. We do need to add a 2 here to balance our reaction, as well as a 2 here. Okay, so now we have our reaction complete. So now that our reaction is complete, let's record the important info from the problem. So it said that we have 38.55 milliliters of HCl, and that was reacting with 2.150 grams of the sodium carbonate. So it's asking what is the molarity of the HCl solution, okay? Now remember that molarity is equal moles per liter. Specifically, this would be moles of HCl per liters of solution. So if we want to figure out the molarity of the HCl, that means we need to figure out how many moles of HCl are involved, and then we'll incorporate this volume down here after we convert it to liters to find our value. So for our stoichiometry, we're going to need to take our 2.15 grams of our sodium carbonate that were dissolved in water, and we're going to convert those 2.15 grams to moles of HCl, because if we can get to moles of HCl, we'll have our answer right there. So let's show that part. So I'm going to start with my 2.15 grams of sodium carbonate. If we already have grams, that means we just need to use molar mass to convert from grams to moles. So our molar mass of Na2CO3 would be this. All right, and now that we have our mole values, let's look to our balanced equation. There's nothing here, so that's really a 1. So for every 1 mole of Na2CO3, 2 moles of HCl reacted along with that. Now, we're not going to go all the way to grams because grams do not show up in our molarity formula. Moles do, so we're actually going to stop right here because at this point, we'd be left with moles of HCl. 2.150 has 4 sig figs, so to 4 significant figures, we would get this. Now, keep in mind, when I do my calculations, I'm keeping the raw number in my calculator, but I'm just writing down the correct number of sig figs now, so I don't have to worry about it later. Okay, so then for our final step, now that we know our mole value, I would do this. Molarity equals moles of solute per liter of solution. Our mole value would be 0.04057, again using the raw number that I had originally, divided by my volume, which remember 38.55 milliliters. If we do our quick conversion here, in case you didn't do that in your head, that would come out to be 0.03855 liters. I'll put that in the bottom. Now, if I divide those two, both of them have 4 significant figures, so to 4 significant figures, our final answer would be 1.052 molar HCl. Technically, you could write moles per liter instead of molar, but there we are with our solution for example 4.28. We have one example left. Okay, so looking at our final example here, so it's very long word-wise compared to some of the others, but essentially it's the same concepts we've already seen in other examples. This one is going to be very similar, for example, to example 4.25 as well as example 4.27. Okay, so if we figure out our type of reaction, we can eliminate precipitation right away because we don't see a solid forming on the product side, so we know that that doesn't make sense. We can eliminate gas forming because there's no gas being formed there. Now, between acid, base, and redox, none of those reactants are an acid or a base, but the real giveaway is that I see iron going from +2 on the left to +3 on the right. I also would notice, if I chose to figure this out, that our manganese is going from +7 to +2. So that indicates that this is a redox reaction in this case, okay? But now let's actually get into the solving of our problem. So let me get this other stuff out of here and we'll get to our problem. Okay, so we already have our reaction here written. It says that we have a 0.598 gram sample of the iron-containing compound, which means that really our mass here is going to involve that. Okay. We also know that we had 22.25 milliliters of this potassium permanganate solution, which had this molarity. Now, remember, potassium permanganate would dissociate into one potassium and one permanganate ion, so if this is the concentration of my whole compound, this would also be the concentration of our manganate ion because, because they are dissociating in a 1-to-1 ratio. Okay, so the question is actually asking what is the mass percent of iron in the sample, meaning we need to figure out a mass of just the iron so that we can divide that by the mass here of our sorry about that interruption with the announcements, but that means we need to figure out the mass of just the iron, and we're going to divide that by this 0.598 grams, which is the mass of our total iron-containing compound, okay? All right, so we're going to start this the same way we started some of the previous ones. Because we have a molarity information and a volume, we can use that to figure out the moles of permanganate ion, which we can then use to convert to moles of iron. Once we get to moles of iron, we convert that to grams of iron, and then we'll finish with our percent step, okay? So to start us off, we will need to start with our 22.25 milliliters of our permanganate ion. Okay, once we have that, we know that we would need to convert to liters, so 1,000 milliliters per 1 liter. Then we can use our molarity. So 1 liter of solution would have 0.0123 moles of the permanganate ion based on the molarity we were given. Then we can use our mole ratio. So looking at our balanced equation here, for every 1 mole of permanganate ion, there are 5 moles of this iron 2 ion as well. So for our ratio, we would write that as 1 mole of permanganate ion per 5 moles of the iron 2 ion. And then our final step would be to go from moles to grams. Now, even though it's an ion, we're still using the regular molar mass of iron, not accounting for those 2 electrons or anything, so you don't have to worry about subtracting from the mass or anything like that. It's still iron, so the mass is iron right off the periodic table, okay? So, if we do our math here, based on our significant figures, this value here had 4 significant figures and our molarity had 3, so 3 would be the limiting number. So to 3 significant figures, we would get 0.0764 grams of iron Okay, so in other words, that's how many grams of iron ion we would have in our compound. So since it really said that this was 0.598 grams of an iron-containing compound, our final step to get our percent value here would be to do that our percent of iron would be equal to the mass of just the iron, the 0.0764 grams, divided by the total mass of our iron-containing compound, our 0.598 grams, multiplied by 100, and then still keeping to three significant figures, we would see that this would be 12.8% iron. All right, so there is our final answer for example 4.29. So as you can see, anytime you're mixing stoichiometry with solutions, essentially you're using molarity and volume data to figure out moles. Once you get to moles, you can go to whatever particular final unit the question asks for, whether that's a mass, whether it's another molarity, whether it's a volume, etc. Okay, so good luck.